So I cannot delete this thing at all. Um, Maybe today it'll get deleted. I don't know. But you want to download or get this finished equilibrium topics and discuss Gibbs free energy. And then tomorrow again, you want to do the multiple choice and the free response. Now, let me ask you guys this: those of you that are juniors, am I asking too much for this week? You guys are good. I just want to make sure. All right. Um, IB is even here. You here? Worst student ever. He's gonna watch this later and feel bad, hopefully. Yeah, IB today, tomorrow actually you were supposed to just work on your IA. And I've got good news because the IA may be the only thing that's going on with IB. Word, yeah, in class Zoom. Friday, finish any question on equilibrium and discuss the start of the next topic. Next topic is acids, bases. We only have two more topics for AP chemistry. They're long. Um, and I kind of want next week. I want to take a break, and I think I want to do a lab because I don't think any of you guys have done it. It's the equilibrium lab, and because of last year, by the time we studied equilibrium max chemistry, we were already in lockdown. And if you were a senior, you may have done it, depending on your teacher. But kind of want to get some type of lab done. Get some more hands-on stuff, and that means those of you at home would be then watching somebody perform the lab. So we'll see about that. No exam next week as we have Monday and Tuesday off. Um, some of you guys didn't do any exams, like out of the we said that you need to do four. I'm sorry, you need to do two out of the four. Some of you didn't do any, so that grade's missing right now. That will be replaced, and those of you that have done the two, remember I take the highest out of the four in a sense. That's good. All right, let's turn on the visualizer. Oh, yesterday, my biggest moment yesterday during the exam was I actually scored a PS5, the elusive PS5. Between test 2 and 3, I was jumping up and down. I was happy. The students I had at the time were not as happy as me. Piper, can you hear me now?
Yeah, I can now, but for some reason
Okay.
I couldn't hear you for like a good 2 minutes.
Did you miss the whole birthday song? Do we need to replay that?
No, I heard that.
Okay. I was just making sure. Did you hear about Emma's scoring of the axe throwing?
Yes, I did.
Didn't sound impressed as we were, did she?
I'm impressed.
Okay, good. You know that if it was Ninja Stars, I would probably do better. Or she's not answering that. She doesn't believe that, maybe. I don't know. All right. Let's see what we got here. So, wow, you guys, everybody took a copy. Did you guys split it up equally? That looks stupid, doesn't it? Hey, it's not what I want though. Piper, will you go on the field trip to watch the Ninja Stars at least? If we do that, yeah.
Sure.
Prove to her that I can throw Ninja Stars better than you can throw Axis. I'm assuming. Good, good. Are you a junior?
Yeah.
Yeah, it's gonna work out because I probably won't be able to get a field trip going on until next year. According to the snow ski club, we have illegitimate meetings, according to some members, not sanctioned. Do you guys realize how cold it's getting, right? Like, is there something going on this weekend? Because there should be, because they probably have more snow now than they had in December. You didn't go. Who's become the leader? Evan acted like he was this year, right? which one's more charismatic, which one is like above and beyond the leader. Out of the two of them, yeah, right. So, as senior president, are you going to take over the club? Are you junior or senior president? Junior president. Senior coup. All right. All right, guys. So let's take a look at this. Hopefully, at this point, we understand that at equilibrium, if K or is greater than 1, products are favored. If K is less than 1, reactants are favored. So during a KSP or you take some type of solid, and that's one of the things you guys are going to have to do is get this solubility chart down. The main things, again, with this are group 1A, all are very readily soluble, ammonium readily soluble, and then anything with nitrate is soluble. Some of these other ones are a little bit more difficult, but you know, if you learn like chlorides and sulfates and hydroxides, you probably will be good. But these guys, if K is less than 1, then reactant. Is that too loud over there? Whatever you're talking about. You good? Good. Reactants are favored. So whenever it comes down to dropping solids into solution, unsaturated is a very low amount of solids. You could literally take the smallest amount you can think of, smallest amount you can measure, drop it in, and that would be an unsaturated solution. The thing is that it's unsaturated until it gets up to saturated, which is equal to the molar solubility of a compound. And that's that KSP that we talk about, like that solubility product constant. That is, whenever we do that, if we figure out the concentration of 1 mole of the substance, that's the molar solubility. If it's above that KSP, that's what we call supersaturated. Now, the thing about supersaturated solutions is they don't exist very long. We can get certain things to be supersaturated, but that leads to like rock candy and stuff like that, or those hot mitts. If you're in the ski club, maybe you have those hot mitts where you bend them and then they solidify and then they release energy. They're exothermic. So if we take a look, if Q is less than K, the system is not at equilibrium. Unsaturated if Q is less than K. If Q is equal to K, that is saturated. If Q is greater than K, then that is supersaturated. A precipitate forms when the system is supersaturated. So let's take a look at this thing right here. What is the molar solubility of strontium sulfate in pure water? So when you look at molar solubility, the biggest thing is you need to make your rice table so there we go with that. So that means that initially all we have is this, and we have 0 and 0 of this. Now, if you want to make a rice table, you can. I know that with this amount of real estate down here, I'm not going to have room to make a rice table, and I can see that this will be plus X and this will be plus X. And since this is solid, this will be 1. We'll ignore this since this is solid. So basically, we're going to get KSP equals, this is plus X, this is plus X, because we have 1 mole of each. All right. Please, if you have questions during this, I know that, like, the thing is, if you get lost early, it's ugly. So this breaks down into 1 of these and 1 of these for every 1 of these. This is 1 mole for 1 mole for 1 mole. So that means that we will get x times x, which is x squared. And that is equal to the SO4, the KSP, which is 7.6 times 10 to the negative 7. Oh no. Boom. TI-84 in the house. So let's do it. So we take 7.6. You guys can follow along. You guys have no idea what picture page is, right? That was when Bill Cosby was actually considered to be a decent human being. All right. Square root. Okay, if x squared equals 7.6 times 10 to the negative 7th, square root of that, we get 1.59. 1.59. Is that right? Times 10 to the negative 7th, right? So that equals x, which means that equals the concentration of SR2 plus and SO4 2 negative. X squared. Square root 7.6 times 10 to the negative 7. Oh, what happened there? You guys are better at these calculators than I am. That was that whole weird thing I had where it was like trying to like squeeze the box. So there's our actual answer. Sorry about that. Apparently, according to Dylan, I only put it over the 7. Where were you on that, Hayden? That's Hayden even in here. You in here, Hayden? Hayden? Man, I do need to start taking attendance, don't I? Hayden Monk. So that is the molar solubility. Now, the reason why this is the molar solubility, this is a concentration of SR you would get and the concentration of SO4 you would get. That means that when this is dissolving, the maximum molarity, the maximum amount of moles per liter that you could dissolve of this substance is 8.7 times 10 to the negative 4th at these conditions for the volume you have, right, and the temperature you have. Moles per liter. This is the maximum amount that you could do. Now we do know that temperature does change K, so it changes KSP just as it changes the K of a reversible reaction. So you get 8.7 times 10 to the negative 4th for that. So then if we do B, we're going to do the exact same thing. And AP calls this scaffolding. So basically, they're going to have us do the same thing for both of these. And then they're going to have us do something with both of them. And then we're going to have to compare them. And one of the things that makes this one different than the other one is that there are 2 F's. Now, we do know that F is diatomic, but that is not the case here because it has dissociated. That means that it's broken apart, means water has basically pulled it off. So instead of putting F2 here, we're going to put 2F minus because that is diatomic. What does that change about our KSP? Well, we have 7.9 times 10 to the negative 10 equals SR2 plus is going to be the same, but what are we going to have to do this F negative? Thank you. And keep in mind, we do need to keep that 2 there because the concentration of this is double the concentration of that. Because when this broke off, for every one of these, we get one of these SRs, but we get 2 of these Fs. So that becomes x times 2x squared. Anybody? 2 is squared is 4. 4x squared times x is cubed. Is Hayden Monk really not out there? I probably should be taking a minute. What? Sam, text Hayden. I'm sure that there's teachers that's their biggest thing. I can't see myself getting that worked up about it. 7.9 times, I should probably record that, should I? 7.9 times 10 to the negative 10 divided by 4. And then we'll take the cube root of that. How do you guys do this? Do you take it to the 1/3? Is that better? Math. Cube root right there. Answer. 5.8 times 10 to the negative 4th. So that is the molar solubility of the SRF2. That means that if you take this at this temperature, you can dissolve 5.8 times 10 to the negative 4th moles per liter. But let me ask you this. Are either of these processes really favorable for dissolving these substances? Look at their KSPs, right? If their KSP is greater than 1, then it's favorable. If their KSP is greater than 1 times 10 to the 3rd, it's almost going to completion. These are way less than that. These are to the negative 3rd. So only a little bit of these are going to dissolve. That means that if you tried this, you would have a clunk of solid in the bottom of the container. C, an aqueous solution of strontium nitrate is added slowly to 1 liter of well-stirred solution containing 0.20 moles of 0.020 moles of F and 0.1 moles of SO4. You may assume that the added strontium nitrate solution does not materially affect the volume of the solution. So with this, we're going to have to make an actual reaction, right? So let's do each one of these. We'll do this one first. SrSO4 yields SR2 plus SO4 2 negative. So if we do this, we are adding this nitrate to a solution. We want to see which of these salts precipitate first. Will it be the strontium sulfate or will it be the strontium fluoride? Well, here's the thing. We already have some sulfate here. We already have 0.10, right? So we're looking as we add this strontium nitrate. Here's the thing I think that was asked. Maybe it was you, but how do we know what's going on here? Well, this is strontium nitrate. So what do nitrates do when they're put into water? They dissociate. They are highly soluble, right? So that means that strontium and nitrate are going to break up. What does that mean? Well, that means that we are increasing the concentration of strontium. And if we increase the concentration of strontium, and this equation can occur, it will favor the reverse reaction, right? So we've got to check by having this already in there, what will adding with the sulfate molecule in there, the polyatomic ion, what will add strontium nitrate do to this substance? Well, we've got to check that out. As the amount of strontium increases, we can assume that this might go up. The precipitate may form. So with that, we are going to take 0.10 and we are going to add x. Oh, I'm sorry. Let's see. Let me think about this for a second. We would minus x. We would minus x. This is 0. This is 0 because this solution just contains these and we're adding this. So this would be plus x. So if we take that KSP, which was 7.6 times 10 to the negative 7, this would be 0.10 minus x, and x. So then
I thought that the first one was a solid.
this is a solid. We have 0 of it at this point. You mean this thing?
Why is there an X though?
What's that?
Why is there an X if there's a solid?
So what we're doing is we're actually making this, and let me check. It actually doesn't ask how many moles that we are making, but if it did, we would, if we know the number of moles that we use up here, that would be the number of moles of the solid we would make. So I think what you're thinking is when we use this in the equation, it will be over 1.
Okay, thanks.
Yep. So if we take a look, 7.6 times 10 to the negative 7th. And if we take a look here, we have x and 0.10 minus x. And again, basically, all we want is the number of moles. So we don't have to deal with the negative here because it's going to use this up to make this. So while one is going down, the other one's going up, they're going to be equal to each other. So if we take a look at that, are we going to need this x right here? Look at how small this number is. And if you want to use it, you can do the quadratic equation. But in reality, what can we do with it? Ignore it, right? Anytime we're adding or subtracting x on this, we can basically ignore it. So what that means is we're going to take, well, we can do this in our head probably, 7.6 times 10 to the negative 7 and divide it by 0.1. What does that become? 7.6 times 10 to the negative 6. As always, you guys are much better than the math at me on this one. So that means that we will get 7.6 times 10 to the negative 6. Right? So basically, that's what we're looking for. If we can reach that, then we would have that precipitation occur. In the first solution, when the precipitate, we'll get there. So the other part of this is we got to check the other one because it's asking which precipitates first. So we will do the same thing with SRF2 yielding SR2 plus and 2F negative. So with that again, we have to start with 0.020. Right there. We're starting with that amount. And the molar solubility for that is 7.9 times 10 to the negative 10. So again, we have 0.020 minus x and x. Again, what are we going to do with that x? Ignore it. So we get 7.9 times 10 to the negative 10. Yes. We have to square it. Thank you. So what does that mean? How do we want to mathematically do this if we ignore this? We square 0.020 and then we divide by it, right? Divided by 0.020. Right. Yeah? Or is there something wrong with that? For every one of these, there are two of these. But guess what? We can ignore 2x as well, right? We're going to know that as well. So we get 1.975 times 10 to the negative 6th. So essentially, this becomes the same as this because we are ignoring that. So that rounds to 2.0 times 10 to the negative 6th. So we take a look up here. Which one did we reach faster? 2.0 times 10 to the negative 6 or 7.6 times 10 to the negative 6? Which one is lower? They're not negative. They're both to the negative 6. So 7.6 or 2.0, which one is lower? Huh? 2.0, right? So keep in mind, they're both at the same power and they're not negative. So 2.0 is lower. So that's the one that we're going to reach first. So which will precipitate first? The one that has the molar solubility of 2.0 times 10 to the negative 6, which is the fluoride, right? So which precipitates first? Sulfur, strontium fluoride. What is the concentration of the strontium ion in the solution when the first precipitation begins? Well, if we're looking at that, the strontium will form when the concentration becomes 2.0 times 10 to the negative 6, because that's the molar solubility. As more strontium nitrate is added to the mixture in C, a second precipitate begins to form. At that stage, what percent of the anion of the first precipitate remains in the solution? We don't have much room there. So let's go up here. So if we take a look, what's the second one that's going to form? Well, whenever that molar solubility becomes 7.6 times 10 to the negative 6, strontium sulfate will begin to form. What is it? 7.6 times 10 to the negative 6. So what we've got to look at then is we have the strontium 2+ ion concentration has to equal 7.6 times 10 to the negative 6 moles per liter. That's when this is going to form. So if we take a look, we have KSP equals SR2 plus and SO4 negative 2. So what of these do we know? We know KSP for this is 7.6 times 10 to the negative. Well, let's take a look. What is the concentration of the strontium ion in the solution when the first precipitate begins to form? So that means that the KSP for the, oh, we already got that. Let's see. Let's take a look. KSP of this versus this. We got that as 2.0 times 10 to the negative 6 for x. So that's that. So we're doing D. As more of this is added, a second precipitate begins to form. At that stage, what is the percent of the ion of the first precipitate remains in the solution? So we want the KSP for this one to be equal to 7.9 times 10 to the negative 10th. And the strontium will be that 7.6, because that's when that's going to occur, times 10 to the negative 6th. And we need to figure out what the fluoride ion is. Am I going to get cut off? Maybe not. So we have this setup. This again is the strontium. This is the fluoride. So we have this, this is the solution we're looking for, and this is the concentration we're looking for, and this is squared. So to solve for this, we're going to divide by 7.6 times 10 to the negative 6th, and then we're going to square root the whole thing. We get 0.010. 2. We only have 2 significant digits, so we'll run around that to 2 in the end. And that is equal to the molarity of the fluoride ion. So what percentage, and this is the weird thing, is they always ask like weird questions like this, but what percentage of this is there? Well, how much did we have at the beginning? 0.20 moles of moles per liter of F negative. So to find the percent, we take the part divided by the whole. And you guys could probably do that in your head. We multiply it by 100. What's 0.01 divided by 0.02? What is 1 over 2? Half. What is half of 100? 50%. That's probably going to do it for us. That's cool, because basically that finishes up our study on equilibrium, except for acid bases and the other stuff, the Gibbs free energy. If you've already done the actual work for the MC or multiple choice question, let's see if I can't pull that up quick as like an awesome teacher move. Unless you guys want to hear more. No, I pressed the wrong button. Maybe we need to hear more about your birthday party. How many people were at your birthday party? Are you at risk now? There's your what? Your bubble. Oh, you've got to click. Is that what we're doing? No, you don't call them clicks anymore. I get you. Is this unit 7? 15%? I got like 2 minutes. This is going to be perfect, I think. I think you guys are going to be impressed if the computer was faster. So let's take a look at these guys real quick. Can you see that? Yeah, I'm not impressed with the computer right now. Come on now. Give me question 30. Diego, is your computer this slow?
What do you mean?
No, I mean, look at this. I'm like typing this thing, I'm pressing it, and I get nothing.
Oh, it's super slow.
Right?
No, yeah, mine's not like that.
Come on. Give me something. Give me question 31 then. All right. So take a look at this. This is interesting. And I know that we're pushing the bubble here. But if we take a look, CaF2 dissolves in water according to this equation. That forms 2F negative. What is in water? Remember from our acid base unit, water self-ionizes. So you have H3O plus and you have OH negative, right? F negative is going to be attracted hugely by H3O plus to make HF. That is a very weak acid. What do we know about weak acids? They do not dissociate. So once that forms, that's going to hold together. So that makes sense that as we lower pH, we have more H3O plus, which means we're going to make more HF negative, which is going to fuel this. This is going to cause this to dissolve better because we're pulling the F negative out of solution by making HF, right? So that's that one. If we take a look here, again, this pH thing, we're going to discuss this on Friday, but I want to make sure you guys get it. We know absorbance. We've done a laboratory on that. So as absorbance increases, that means the concentration is increasing of whatever we're making, right? So in this case, the absorbance for the copper hydroxide changes. As the pH goes down, we know the H positive goes up, which means that the OH negative is going to be pulled out, just like the F negative. So it's going to produce more being dissolved. And we'll cover that Friday, guys. Good luck on the ice step tomorrow if you have to take it. Hopefully you have, well, you won't be here. So we'll actually get started on time on Friday. No. That's awesome. I'm glad that you got to experience that. I think I have. Have you done?